In December 2022, scientists got more energy out of a fusion reaction than they put into it. And that's genuinely impressive, but it's also only one small piece of a very large puzzle. Fusion is the process that powers the sun. You take two light atoms, squeeze them together hard enough, and they merge into a heavier atom, releasing a burst of energy in the process. The atoms used in most fusion experiments are deuterium and tritium, both forms of hydrogen. Deuterium comes from seawater. Tritium is rarer, but it can be made from a metal called lithium. The fuel itself is not the hard part. The hard part is that fusion only happens at temperatures hotter than the core of the sun, around 100 million degrees Celsius. At that temperature, matter becomes a plasma, which is basically a superheated soup of charged particles. At the National Ignition Facility in California, scientists use 192 giant lasers to compress a tiny pellet of fuel from all sides at once. The goal is to squeeze it so fast and so hard that fusion happens before the pellet flies apart. In December 2022, they crossed a threshold called ignition. The fusion reaction released about 3.15 megajoules of energy, while the lasers delivered about 2.05 megajoules to the target. That's a real energy gain, more out than in. That milestone matters because it proved the physics works at this scale. For decades, people debated whether laser-driven fusion could even reach ignition. Now there's no debate, but here's where the numbers get complicated. Those 192 lasers consumed around 300 megajoules of electricity from the wall to produce that 2.05 megajoules delivered to the target. So the overall system used roughly 150 times more energy than the reaction released. That gap between the physics win and the engineering reality is enormous. To actually power homes, a fusion plant would need to produce far more energy than the entire system consumes. Lasers, cooling, control electronics, everything. A separate approach uses magnetic fields instead of lasers to hold plasma in place long enough for fusion to occur. Devices called tokamaks do this with a donut-shaped magnetic cage. ITER, a massive international tokamak being built in France, is designed to test whether this approach can produce 10 times more energy than it puts in. Both approaches still face serious engineering problems that have nothing to do with the physics. How do you build materials that survive being bombarded by high-energy neutrons for years? How do you breed enough tritium fuel inside the reactor itself? How do you do any of this at a cost that makes sense? These are not small details. They are decade-scale engineering challenges that require completely new materials, new manufacturing techniques, and a lot of trial and error. Several private companies are now betting real money that they can solve these problems faster than government programs. Some aim to have demonstration plants running in the 2030s. Whether that timeline holds is genuinely unknown. Researchers are honest about that uncertainty. What ignition at NIF actually proved is that a fundamental piece of the physics is real and achievable. That's worth celebrating. What it didn't prove is that fusion power is around the corner, because the distance between a physics result and a working power plant is measured in engineering, not equations. If you want to understand what those engineering problems actually look like up close, the tokamak story goes much deeper. And it's worth following as ITER gets closer to its first plasma.